Good morning.
I couldn't do my homework this week, so can I have it on Wednesday?
Yeah, give it time for that. Busy?
Yeah. Is Ria still coming today?
Ria?
Yeah. The one that was.
Yeah, I don't know. No, I haven't been told, so I assume she's coming.
Okay.
Yeah, so if she's not, she probably, her mom will probably call me. Yeah, I haven't heard anything. Okay, module 2 book. Okay. Is there Esther? Is it Esther?
Who's this?
I mean, is it Ria?
Via.
Okay, Ria. Okay. Oh, hello. We just talked about you. Module 2. Must be Ashley. Morning, Ashley. Is Brendan here?
Yeah.
Okay, I just need to say hello. Hello, Brendan. How are you?
I'm good.
Feeling better? Hello, Lara. Feeling better?
Yeah. Back to normal.
Okay. COVID, yeah, I know. I told you it's spreading around. Yeah. Okay, good to see you again.
You too.
All right. The answers should be uploaded there. I made up folders for each of the chapters. I mean, like those subjects. So let me know if you can find the subjects.
Yep.
Okay. And yeah, it's all there. You're right. Ooh, sitting over there. Okay. All right. Module 2. And just Anna. Okay, first of all, okay, give you something to give you, okay? Homework, Christine. All right. This is homework. It would be great if that was your homework, wasn't it? Oh, okay. Ria, yeah, so true that. Christine, Ara, and just waiting for Anna to come. Hello, Anna. Yep, have a seat, please. Got 2 things to give you.
So good.
That's your work, module 2 workbook for you. Okay, let's, for the next 5 minutes. Oh, sorry, okay. That. Okay. Next 5 minutes, have a look at your module test. Well, ask me if you need to get some extra marks, okay? Or ask any questions about that test. So, I mean, I went through the questions, but I'm happy to go through some of the questions before we start module 2. What's this test 2? Is there any questions do you want me to go through, or do you want to argue? Do you want to discuss about the marking? Yeah.
For 18C, like two sources of error, couldn't there be like an error in like statistics?
What do you mean by the statistical error?
It's like if one of the equipment isn't like calibrated properly.
You mean systematic error?
Yeah, a systematic error. Okay.
As I said, there are only two types of errors, whether it be systematic, random. No human error, no human error, no statistical error. Like that sort of be more, it's something dealing with the uncalibrated tools. Yeah, that's a systematic error then. Guys, what happened? That wasn't too bad. The paper wasn't too bad, was it? Was it bad? Okay. I know some of you not really prepared some radioactive isotopes, like example the cobalt-60 and some other things too. So, as I said, that's the kind of topic that you can study like night before the exam. Like you don't really need to worry about like the whole terms. If you got your assessment schedules, okay, share that with me. And all right, is your chemistry teacher Miss Carr?
No.
Okay, just wondering. Yeah.
I think he's teaching chem this year.
Oh, okay. Oh, because I found that she's making it really harsh. Yeah. Okay. It's a good news. And I found out your school you're going out of excursions. Yeah, and then you got to get some depth study about the excursion. So just be mindful. Yeah, okay, when you go to excursion. If you started getting some notification about like depth study, like let me know. It might be the report writing. It might be I don't know, like a test, in-class test. It could be a skills test. It can vary. Okay, so depth study doesn't always mean like writing the report. I know most of the girls, you guys started module 2. Okay, so we're going to start the module 2, which is good. If you need some extra question for stoichiometry or some practice questions, and let me know. Okay, I can print many for you. Okay, and I give it to you too. Okay, and if you want to stay back and discuss about some of the questions, I'm more than happy to stay back. Okay, if you only have any questions. And you okay, Ria? Okay, any questions from the test? No. Guys, reflect yourself why you lost so many marks. It's not because probably not because of like you didn't know the contents. It's probably because of like you didn't get the full mark for many of the questions. And this is the important thing about studying examinations. You need to know how to write to get the full mark, not the 2 out of 3, 1 out of 3. That's not what we're aiming for. Okay, that's hard. That's something we need to practice in year 11 so that we can like boost it up in like year 12. You don't need to worry about in year 12 to how to write the answers. Later on in HSA, you get the 7, 8, 9 markers. In one question is 9 marks. It means that in your head, you probably need to structure the how you're going to write the answer for 9 markers. It's basically writing an essay. You need to write about 2 pages up to 3 pages in chemistry. And that requires some structures. So I will explain the how to think about the 9 marker, 4 marker, 6 marker. That's more like exam techniques. But don't worry, we have lots of chances to discuss about many of the questions, especially in the year 12 later on. No questions? No questions for this paper, Ara? Maria? Christine? Good? Ashley's looking really hard because she doesn't need a 1 mark, I know. Okay. If you cannot find it, okay, you need to tell your time you can come back for your retest. Okay. Aim high for the retest. Try to get above like 80%, of course. But if you can get up to like 90% of the retest, I mean, module 1's done. You don't really need to worry about module 1 a lot after that too. Okay. So I will ask the time and availability for your retest after class today. So think about it when you're available. Okay, no questions? All right, let's start module 2. Module two is the not the most interesting, to be honest, but this is the most important topic of the module of the whole year 11 and 12 because, and I would say this is the real start of the year 11 content because I know some schools covering the moles and a bit of stoichiometry in year 10, but not many schools actually doing that in year 10 chemistry. So we're finally starting the year 11 contents, but it uses some of the things that we used in the year 10 and the previous in the module 1 as well too. So the first thing we need to understand for this chapter is, 1, you need to know how to balancing the chemical equations. The 2, you need to write the states of the chemicals. Now, let's have a think about some questions that we have. Page 2, please, the balance in the chemical equations. So, balance in chemical equations is based on this, based on the conservation. The conservation of the mass in the chemical reactions. This means that when we have a certain amount of mass of the reactant, this must be same as the mass of the product. This is how we can define the conservation of the mass in the chemical reaction. So remember that the mass of the reactant, so if you're given 10 grams of the reactant, after the complete reactions, you need to have the same grams of the product, theoretically. Okay? Because we believe that the chemical reactions happen in the closed system. We don't really let the particles move away or move out of the system. So eventually you get the same amount of the reactant products. So why do we need to use that? So basically balancing requires to think about how many molecules and elements we have in the reactants and the product side too. So you probably did that in your 9 and 10, so I'm going to skip quite a bit. So think about the H2 plus O2 producing the H2O. There will be what in total of the reactant side, the hydrogen will be 2 and oxygen we have a 2. Now the product side, you see that hydrogen is 2 but oxygen is 1. In the case of that, we call this unbalanced because I wouldn't say that same number of the hydrogen, oxygen on the reactant and the product side. So the way we can balance that is we can't change the H2O because it's kind of chemically formed. What we only can do is we can just move around with their coefficient values. In other words, we can add something value over here like this. So making that into, I rewrite it over here, H2 plus O2 gas, producing that 2 H2O gas here like that. Now think about adding the 2 in front of the H2O. That makes the total number of the hydrogen be 4 and total number of oxygen to be 2. In that case, you're matching balancing the number of the oxygen but not the hydrogen. So to balance the number of the hydrogen, you just need to times 2 over here like this. Easy. Okay, so a bit of like a mathematical, like I'm playing around with the numbers, and like you would feel like this is kind of playing around with the puzzles, that matching the number 2 and 2, but there's a rule in the puzzle. I'm solving the puzzle question like this. Okay, another thing is from year 11, I don't know about year 10, you are now asked to write the states of the chemicals. And I don't think the schools will provide a brief and detailed explanation about how to write the states. You probably didn't learn that in year 10, and then ironically from year 11 they just give you and write the states. So state rule is something that we can use. So I'm going to give you some brief ideas about state rules. There must be some space. Can you find the space? I'm sure we have a space provided. If not, we can use the separate notes to copy this down, or you can use a space within the page 2 as well too. State rule. Let's write it down here. So remember that we have in total of the 4 states. That is solid, liquid, and gases, and aqueous. So in each of the situations, the solid states, you need to know which elements, which kind of chemical goes to solid, liquid, gas, and aqueous to. So first, let's start from the solid state. That's the symbol of the S. For the solid state, the pure metal element are generally be solid, okay? Except the mercury. Mercury is the only the liquid. So example, what do you mean by the pure metal element? Anything on your periodic tables, on your the right left-hand side periodic table. Say for example, if you have magnesium itself, then more like comes in a solid. Calcium, solid. Even sodium can be a solid. Iron can be solid. Copper, solid. So if you're coming in the pure element metal, then more like it comes as solid state. Make sense? Okay. Exception is the mercury, Hg. This is the only metal that comes out in the liquid state in the room temperature. So state rules. Make sure that at this is basically at 25 degrees Celsius, which is called that room temperature or the standard laboratory conditions there. Okay. In some cases, some ionic compounds, that's basically we call the salt in chemistry, comes out in the solid state or precipitate. So example of that is, we can think about sodium chloride. It can come out of the state of the solid. Remember that means that it comes in the forms of the table salt, or the rock salt forms too. Precipitate, you probably learned that in year 10. There's example of a good example of silver chloride. It comes out in the solid state. And there is a specific rules to find it out which is a precipitate, which is not a precipitate in the ionic compound. We're going to learn that more in details in module 3, but just to give you a clue, just remember the, where's my purple? Okay, just remember this, SNAP, for now, okay? That is sodium, nitrate, ammonium, acetate, potassium. These are the ions that, okay, show you the symbol of that. Sodium, Na+, nitrate, NO3-, ammonium, NH4+, acetate, CH3, potassium, K+. These are the ions that they never form the precipitate. So in a case you're having this, it's more likely that comes out in the aqueous state. Now, sodium chloride is a solid state. Yes, means that we kind of dried it out all the water, basically, in the solution to get the precipitate. It's not a precipitate. That's basically the solid form of the ionic compound. We can actually dry them and make in the solid state as well too. But in forms of precipitate, they never form the precipitate. Okay, for these given here. Okay, that's for the solids. And there'll be no solids in the gases. Gases, like, there's some money. Second, the liquid. The symbol of the L. We do not have many liquid in using in the chemistry. So water is always be more likely, about 90%, 99% would be liquid. The only exception would be water not be aqueous, and the liquid is when the temperatures above the 100. Okay, that's the only case we can consider here, but at 25 degrees Celsius, water comes in H2O. Okay, and some organic compounds can come out in forms of the liquid, like for example, C2H5OH, this is the ethanol. Okay, can come out in the liquid state as well too. Now, don't worry too much about the liquid state of organic compounds until we learn that in module 7 in year 12. For now, you may just think that as only liquid state would be just the water up to year 11 standard now. Because we're going to learn more about those organic compounds in year 12. And then you will see what makes them to be liquid state, what makes them to aqueous state. But for now, just remember this from water. Okay, that's it. 3. Now we have the gas, the symbol of the G. The gaseous state, first of all, the pure diatomic non-metals elements generally comes out in the forms of the gas. For example, N2 gas, H2 gas, O2 gas, CO2 all comes in the gaseous state. Okay. Now, one exception is bromine, Br2. It actually comes in the liquid state or the aqueous. Only this one is the exception. But in that case, the question will provide you that it's actually bromine water, bromine aqueous solutions too. So in that case, it's right in the states. So these are the gaseous states. Okay. Also, some non-metal or covalent compounds can also come in the forms of the gases too. So example of that, CO2 gas, okay, NH3 ammonia gas, and forms like that too. So what you can see there is, most of the non-metals are existing in the forms of the gases at the room temperature, okay, with some exceptions there. Lastly, the aqueous, and you will see the AQ about like 80% of whole like chemical reactions too. This is the ionic compound in solution. Solution is like, you can just simply think about salt water, dissolving salt into water. So example of that, most of the ionic compound, I would say most of the compound, up to like 90% is, ionic compound would be like an aqueous state. Because in a chemical reaction, we are basically dealing with the solution to the solutions rather than solid to the solutions too. So example of that, yes, we can have a sodium chloride, but in the AQ. Okay, and also we get like something like using that potassium nitrate AQ. Now, in the case you have including the SNAP, sodium nitrate, ammonium acetate, potassium, we tend to say that most likely comes in the aqueous state in that reason because they would not form the precipitate in the chemical reactions. So anything out of that, there's a chance of forming the precipitate. Now, for the precipitate, the easiest way to determine that whether there'll be precipitate or not is in your chemistry formula sheet. This is kind of a cheat. Underneath, there's a data sheet called like solubility constant value here. These are most likely a precipitate given. Okay, so this will be given in your school exam in the year 11 and 12. These are the precipitate, about like a 99% too. If it's something having inside there, most likely they are solid. Outside of that, most likely be aqueous too. For now, okay? But there is a solubility table that you might need to memorize later on too. But let's start from the SNAP for now. All good? So remember that most of the ionic compound would be the state of the aqueous in that reason. I forgot to tell you that the solid, there is actually one more in some exception of the some non-metal or covalent lattice. So for example, carbon. We learned about carbon in module 1. That's allotropes, but carbon itself, it comes in the forms of, it can come in the diamonds, which is solid, or the graphite in the solid too. Sulfur can also come in the solid state. Phosphorus can also in the solid state in the pure forms too. In that case, you might see that I'm not writing like numbers at the back. It's a diatomic. That is not a diatomic, so it's kind of indicates that it's a solid state. But in this case of this, the pure some covalent lattice and solid state, most likely a question will provide you that the solid something, solid carbon, solid phosphorus. So you need to follow the question instruction then. Okay, this is a general like a state rules that you have to memorize and understand, but have a think about what we learned in module 1 in detail, especially covalent, ionic, and metallic. So most of the metal comes in solid, just need to remember that. Most of the non-metals comes in the gaseous state. Most of the ionic comes in aqueous state. These are three kind of summary I can give you, like, okay? Only liquid we will get is in the chemical reaction, it's most likely the water. So using that state rules, that means we are able to write all the states. So have a look at these next example given here. H2 plus N2 goes NH3. As you can see from the state, NH2 is diatomic non-metal covalent, which is gas. N2 also be a gas. NH3 also be a gas too. Okay, so start with the rightness states and then balancing that after. So to balance that, the rule for the balancing is, personally, I would put the pure element in the last of your balancing because the pure element is something that is easy to control. So what I do is I start with something more complex molecules or complex ions. So NH3, matching that to the number of the hydrogen to here, we have a 3 and 2. So to make it into the same number, the common factor, you might need to times 2 to make it 6 times 3 on the H2. Once you do that, okay, you just need to figure out N2 number on the reactant and the product side. That's N2 and 2 nitrogen. So this is now balanced. Okay, so we now start to call that, this is the fully balanced equation with the states. States is something, and unfortunately, if you get it wrong with the states, from now on, you get the mark deducted. And teachers are really harsh on the markings. That states. Okay, so let's do some practice on this balancing. Don't worry about this 1.1. This is a really complicated one. We don't really do that. Year 10, I probably gave you that, but let's try it again. Okay, can you write the states and the balancing of those equations, please? And for question 11, I'll give you one more. Once you complete up to the question 10, try to answer the 11, 12, 13, 14, and 15. There's an extra 5 questions on the board too. Excuse me. And all right, before you go to excursion, if you do go to the same place like last year or year before, I'll share their assessment. I actually found that from your school. Yeah, so he didn't do that well, but because he found it really hard in the excursion. And remember, he talked about it, and you got to learn about some indigenous Australian. Yeah, so no one enjoyed it, but. Let me know once you go to the excursion. Give you 3 more minutes. Okay, I started from the number 1. We have Fe plus H2SO4 and moves like 2. Okay, in the case of that, we have a pure metal element. So write it down: state, solid. H2SO4, it's an AQ, it's an acid form. So in the case of that, you get, it forms the aqueous state, which is the solution of the sulfuric acid. Ionic compounds, as I said, about 90%, maybe more than 90% would be AQ. So you can just write it down: state. And then H2, pure non-metal element in the diatomic form, gas here like that. Okay. Now the rule of balancing, you simply just think about like from the most complicated form, which is Fe2SO4 3. If you start from there, you can balance by the ion by times 2 in from the ion, okay, and making that into 3 of the sulfate. Does it make sense? Then in making the total number between just a 1 or just nothing in this case, and then H2, leave that in your last step. So because we have a 6 hydrogen, you need to have 3 of the H2 as well too. Okay, so recommendation is start off with the most complex ions, the compounds you have, and then move that to like the pure, the simplest one. Okay. All right, Anna, what would be the states of the CH4O2, CO2, and H2O then? States. Gas. 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 And the liquid. Good. Easy. Then can you balance these now? 1, 2, and 1 and 2. So it is balanced. Good. The carbon number is balanced, hydrogen number is balanced, oxygen number is balanced. Well done. All right. All right. Oh, lucky you. You got the given the states. Okay. So balancing. 1, 4. Checking that. Yeah. Oxygen's balanced. Silicon's balanced. Yep. Chlorine's balanced as well too. Well done. Okay. Ashley. 4. States. Maybe solid. Yep. Aqueous. It's a solid. It's aqueous. Now, for the silver iodide, this is a thing that you can use your periodic, the data sheets. If it was given, it's actually easier. Find the silver, and silver iodide is on the list over here too. That means that it comes as solid state. Well done. So it's a solid plus aqueous, making the silver sulfite is actually in the part of the sulfite is not really in the list. So using that table, it actually comes in the AQ, but for now just leave the solid because actually they form the precipitate. Later on you need to memorize some of the examples of the silver precipitate too. But for now, just leave that and balancing. 2, 1, 1, and 2. Balanced, balanced, and everything's balanced. Good job. Next one, Christine. State. Aqueous. Could be, yep. Gas. Oh, it'll be gas. Yeah. It'll be liquid. Now, for the ammonia, it can come in the forms of the liquid, aqueous, or the gases too. So ammonia gas can be present, ammonia solution can be present if we dissolve in the water. But for the chemical reaction, we just believe that in the aqueous, doesn't really matter for now. Balancing. 4, 5, 4, 6. Check. Oxygen, we have a 10, 4, 10, 12 hydrogen, 12 hydrogen. Good. Nitrogen is balanced. Okay. Rhea, states are given. So balancing only. 1, 3, 1 and 3. Let's check. 3 carbons, 6 oxygen, 6 oxygen. Balanced. Good. So in the case where you have some special states, they're actually providing the states given over here. For example, iron in here, it comes in liquid. Kind of indicating that this might be happening in a high temperature, like up to 300, 400 degrees Celsius too. So we just following the general rule in 25 degrees Celsius for the states for now. Okay, Anna, what about this? States? It could be a gas, but let's leave it to the AQ for now. Okay, HF? AQ is good. Oh, I had to use blue. AQ. So let's do the AQ. All the solids. AQ, good. Aqueous, and the liquid too. Silicon oxide actually comes forms of this solid because we have using for the semiconductors, making that. And balancing. 1, 4, 1 and 2. Easy. Good. Next one. All right. States of these. AQ, gas, AQ. Okay, it could be a gas, or it could be a liquid, or the AQ. Let's leave the bromine, only exception in like a liquid state, or the non-metal elements. Balancing? 2, 1, and 2 and 1. Good. This is now balanced well. Actually, states. Start. AQ? Yeah, good. Now, this is what I mean by memorizing, oh, it's gone. SNAP, that sodium, potassium nitrate, ammonium acetate. Having the ammonium, having the nitrate means they can't come as forms of solid. So this is why we write the AQ and AQ. Okay, and then there'll be most like a solid and leaving that to the AQ. Good. Balancing? 4, 3, 1, and 4. Yep. Check. 12. Oh, yeah, should be 12. Good. It's balanced in number of the all nitrate, ammonium, phosphate. Good. All right. 10. Christine, states, please.
Gas.
Magnesium hydroxide. That's what? That's ionic compound. That'll be aqueous. Remember that most of chance, 90% will be AQ. Then HCl, AQ. It's good to remember that all these different type of the acid and bases. We probably did in year 10 a little bit, but all the acids comes in the AQ. And when you see like acid, that's AQ. Base, most likely AQ2. Then and liquid. Good. Then states got done and balancing. 1, 2, and 1 and 2. Now it's balanced with all the numbers. Good job. Okay. So it's nothing like, I know this is a bit little tricky to write in the state, but giving a simple summary, most of the ionic compound will be aqueous. If you're not too sure about the state, just write the AQ for the ionic compound, metal and non-metal combinations. Only a few exceptions is you got to think about some precipitate form too. Use that data sheets, most likely, okay, to prove and to see that whether you have it on the list. just for now. We're going to learn that, we're going to touch that a little more in details in Module 3 when you're learning about solubility. Okay? All right. This is something that you probably had in your year 10, and if you learned that in school, like you're probably asked to memorize the template of some of the chemical reactions. For example, complete combustion or combustion of the this hydrocarbon producing that water and CO2. So the way we can write that is C2H5 started from C2H5OH. Now state of that ethanol is given as AQ. And that's reacting with the O2 gas, producing that combustion. Just try to memorize as some sort of template. Complete combustion always produces that water and carbon dioxide. Now, as we discussed that, water will come in the H2O liquid, but for the combustions, this actually comes in the gas because we're producing lots of heat from it. This is a point that is something we need to check with your school teacher. If your teacher say like, write it in the liquid state in the combustion, just follow that. Technically, it should be a gas because that's out of the 25 degrees Celsius. Theoretically and practically, it must be gas. But let's not go against to your marker, okay? It could be one of those. Then CO2, we produce in the gases form too. Once you get those, the numbers right, you just need to balancing it again. Start from the most complicated form, C2H5OH, so making into 2 of the CO2. That increase that number of the oxygen to be 1 and 4, so making the 5. So that's giving you, the hydrogen number is 5, 6, so we need to have a 3 of that. They're having your 3 oxygen, 4 oxygen, 7 on total of the product side, so making 7. You're looking at 1, you need to times 3. This is a combustion reaction of the ethanol then. Okay, the reason why I'm giving you this question is this is something that you will be given from Module 2 and Module 3, that they will provide you not much details about the products because we assume that you learned it in year 10. So they move really quickly on those chemical reaction types. Another type of the chemical reaction that you might need to memorize is the photosynthesis and respiration. Yes, I covered that in biology class, but we do the same thing in chemistry. Guys, just remember that the magic number for the photosynthesis and the respiration is 6. It's multiple of 6. I'll show you what that means. Photosynthesis requires the CO2 gas reacting with the H2O liquid with in the sunlight, in the presence of the light energy, producing the C6H12O6. This is called the glucose. Glucose comes in the AQ state and leaving the O2 gas here like that. Once you get it there, don't try to balance that. Just write the, 6, 6, 6. That's it. This is what I mean, like it's a magic number, 6. 6 is a repetition of the 6, 6, 6, 12, 6, even that inside there too. Okay, it's good to memorize an example as an example of these later on the endothermic reactions in the photosynthesis. Respiration is some forms of the combustion reaction that is using C6H12O6, which is AQ. This is reacting with 6O2. Let's write it down, O2 gas, producing that CO2 and the H2O liquid and the gas. Remember that we need to write it down the relevant state. It will simply be 6, 6, and 6. Easy. Okay, doesn't require any energy because respiration basically we're combusting. We're using that glucose and oxygen to produce the energy. Now, if you remember that the reaction between acid and metals in year 10 again too, okay, that producing that always acid and metals, acid plus metal produce that salt and the H2 gas. If you didn't learn that in year 10, just memorize as a template. You will see that quite a lot from now on too. It's pretty awesome knowledge, as I said, but I can go through some of the details there here. Then hydrochloric acid reacting with the Mg, producing that and MgCl2. Now, this is the aqueous and the H2 gas straight away. Balancing that times 2 on the HCl, now is balanced. Okay, another reaction is acid plus metal carbonate, producing that salt water, and the CO2 gas. That's another template you need to memorize. So if you have a reaction between sulfuric acid and sodium carbonate, it will be reacting as forming the sodium sulfate, Na2SO4. Again, we can get the state of the sodium sulfate straight to the AQ because we have a sodium, which is part of SNAP. Just get the state, state to AQ, right? And then we get the water and the CO2 is produced. Write the state as this. And you just need to balance that. Think about the number of the sulfate, hydrogen, and carbonate. This is actually balanced. Okay, so it's a bit early to talk about some different type of chemical reaction because whole module 3 is about chemical reaction or different type of chemical reactions. We're going to talk more about those templates of the chemical reactions. But states, as I said, if you get it wrong with the state, for example, if you write the gas, if you write the liquid for the CO2 instead of the gas, then you actually lose a mark because of the states. Okay, so be mindful of this and writing the states correctly. Any questions about balancing? Does anyone need more practice on the balancing? I can give you some practice like the balancing sheets, but as we go, you got to do lots of balancing too. You okay, Anna? Good. Okay. All right. Let's now talk about some more about stoichiometry. From now, you will hear lots of those, the term, the stoichiometry, stoichiometry, same thing. Okay. The easiest way to think about stoichiometry is we are basically thinking about balance between two of the reactant and the product. Okay, so thinking about like in a balancing here, we basically stoichiometry is coming out from that we want to balance that the reactant and the product in terms of their mass, in terms of their volumes, in terms of the mass and volumes too. We do not use volumes quite a lot because that's kind of limited. It depends on states. So let's talk about the mass and mass stoichiometry. As I give you some kind of introduction, this is using the conservation. Let's write it down over here, conservation of mass in chemical reactions. Again, that simply means what? The mass of the reactant theoretically must be equal to mass of the products that you have. This is things we're going to use quite a lot when you're describing and show you the working out in chemistry, the calculation question from now to is slightly different to what you need to do for mathematics and physics. But I'm usually you need to write quite a lot to show and get the full mark in the chemistry, like in the calculation questions. So let's go for the example here. Assuming that all reactants are consumed in the following reaction, calculate the mass of the product formed when 46 grams of sodium metal react with the 253.8 grams of solid iodine. What mass of sodium iodine is produced? Okay. I know the question is not relevant to like a stoichiometry, but let's write it down. It's balanced equation from the given information here. You're given sodium metal, that is Na, state ought to be solid. Remember that pure metal element comes as solid. And they react with solid iodine. It's given. So iodine cannot come in a forms of the I itself. It generally comes I2, maybe by just write the I for solid. As I said, for the some covalent lattice, it comes in pure element forms. I2 representing a diatomic of the gaseous state in there. Okay, it will produce that sodium iodide in solid here like this. Okay, that's how you can differentiate. Again, remember the I2 is a gas, I would simply be a solid in the lattice structures. Depends on the structures they have. Molecular lattice again. So the way we can think about the question is this. According to, I got it right here, according to the conservation of mass. We would say that the mass of the reactant is the same as mass of the product. So let's write it down. Mass of the reactant, which is sodium, plus mass of the iodine, must be equals to mass of the sodium iodine, like this. And then you got to show that, as we need to find what mass of sodium iodine is produced, you just need to substitute the relevant values inside. Then what do you have? You got a mass of sodium at 46.0 plus that 253.8. Okay, adding these two up, you get 299.8 grams. Now, another thing, the unit would be grams, by the way. You need to keep on the unit. When you're looking at the question there, you have given two different significant figures. 46.0 is 3 sig figs. 253.8 gram is 4 sig figs. Okay, so I'm going to talk about some of the sig fig rules later on too, but let's write it down over here. It's given on your workbook in the chapter 2, so don't worry about to copy this down. It's given, but I just give you on the board too for solve some question. Sig fig rules is something that's very important in chemistry and physics calculations. So sig fig rules. Okay, when you're adding or subtracting the different sig figs, what you do is you follow the lowest, the decimal point. Okay, so in a case, let's use that for an example, 46.0 plus 253.8. We're following into the lowest sig fig, which is 1 sig fig in this case. So we're going to leave that into 2989.8 in 1 decimal point, like this. Okay, that's the rule for when you're adding and subtracting the different sig figs, following to the with the lowest decimal point. Okay, second, when you are multiplying or dividing the different sig figs, is something that's very important. Sig figures. What do? You follow the lowest, the sig fig in that case. So have a think about it here. If we times 3.0 times 5.79, like this, then what do? You put it into calculator, 3 times 5.79 actually gives you 17.37. Now, if you just write that, it says you get it wrong. You actually get a mark deducted in chemistry. You will mark really harsh on the sig figs. Your answer, as we have about 2 sig figs and 3 sig figs, when you're multiplying those, you need to follow the lowest sig figs that you have, which is 2. So that means it needs to be 17. If that's a grams, write in the grams or liters whatsoever. Okay? Now, tricky part is sometimes you're given 1 sig fig. And I really hate to write it a 1 sig fig value because that causes a lot of sig fig errors too. But if you're given 1 sig fig in your question, follow the 1 sig fig. Okay? There was one school that was marking on the 1 sig fig. I don't know why. And yeah. And then people got it wrong because they wrote sig fig, 2 sig figs, 3 sig figs. So follow to the sig figs you're given. In a case you're given something, some of the constant values in your formula sheet over here, they're more likely to come at 4 sig fig, 3 sig figs too. Yes, it's recommended to follow that low sig fig as well too. So generally, you will get the answers in 2 or 3 sig figs in chemistry, but depends. It could be a 1, could be 4, depends too. Now, another rule for that is when you're having a log values, this is something that I'm going to talk about in later on in module 6 in the chemistry. The log values, we only count, it's good to write it down, remember that, for the logs, for log values, the decimal point is only considered as the sig figs. So what that means, if you have a log 10, so like a pH is a good example of that, so later on too. You've got to see lots of pHs sometimes too. Or sometimes you can use that to determine the sig fig from here. If the pH given as 1.0, it looked like 2 sig fig, this is actually 1 sig fig. Okay, pH say like 3.52, that's a 2 sig figs. Okay, we only count the number at the back as the sig fig in the pH or the log values too. The reason why I said that is in those girls, you guys are really tricky on, strict on the pH calculation and some of the sig figs later on too. So be mindful. Okay, don't get it wrong. Okay, all right. This is why your answer for the example is it should be living in 299.8 grams. And good to show you that in the bracket, this is a 1 decimal point. That's indicating that I follow the sig fig rules. I know about the sig fig rules. Okay, let's do the example 2. Assuming that all reactants are consumed in the following reactions, calculate the mass of the reactant consumed. In this case, we have a solid iodine Ni2, it's given. Now, react with sufficient sodium metals to produce 99.9 grams of sodium iodine. What mass of sodium is consumed? So, you don't have to provide the balance equation in this case, we don't really use the equation, but what you can tell is, you can just recommend to show, as is given, let's follow that, producing the NaI solid times 2 to balance this one out. Then, after you got to write, the reason why we need to write the balance equation is we need to determine that which is on your reactant, which is on your product side. Pretty easy. Means that, again, write this one again, the rule according to the conservation of the mass, make sure you provide that in details. The mass of the sodium plus mass of the iodine, it should be equal to mass of sodium iodine, which is the product side. The question is then asking you the sodium, so therefore mass of the sodium is found by mass of the sodium iodide minus mass of the I2 here like this. Alright, then show the substitution. So we have a sodium iodide, it's an iodide, should be 99.9 minus sodium, solid iodine is 84.6. Okay, minus these two values, you would get 315, so 115.3 grams in 3 sig figs. This will be your final answer then. Okay, now what you need to concern from your writing, the working at the chemistry is you need to show, if you know the rules, if you know the formulas and using that in that question, in the answers, you need to show that all the relevant formulas and the laws or the rules. Even though, I know, it makes your hands hurt. Sometimes you write quite a lot of those too. Okay, that's the main difference between probably the mathematics to the chemistry. Okay, now, could you try for 1.2 A and B now, please? Does anyone need a calculator? Yep. Bring your calculator next week. We've got to do lots of the calculations. So, I know just chemistry, but we've got to starting that quantitative analysis. Sorry, the calculations. Okay, question A. One student measures the 34.5 grams of the sodium and reacts it with the 380.7 grams of iodine, which is all consumed, producing the 15.2 grams of sodium iodine. So let's write it down. Student 1, result, student 1. The mass of the sodium he used was given as 34.5 grams. Mass of the iodine was, he used 380.7 grams, and mass of the sodium iodide he produced was 415.2 grams, given here like that. So what you realize it is, when you add these two, it's making the same number, 415.2. So this is following to the conservation of mass, as we can see from the numbers there. So, got to think about here. It is kind of fixed number. From now on, this is a kind of fixed the ratio. That if you're given 34.5 grams, it needs to have 380.7 grams all the way, because we know that this is for the complete reaction. Complete reaction means that we're not leaving any of the reactants, making the full products that have completed the whole reaction itself too. Okay. Now, student 2 then use something different too here. Student 2, same amount of the sodium. So he used mass of sodium. He used what's 34.5 grams, but instead of the 380.7, he used 450 grams. So this is the main difference. Okay, but he realized that it produced the same amount of sodium iodide, that is, again, 415.2 grams here like this. Okay, remember that for the student 1, this is for the complete reaction. They're not leaving any of the reactants. So the ratio between the mass ratio between sodium to iodide must be 34.5 to 308.7. This means for 304.5 grams of the sodium, 380.7 grams of the iodine is required for the complete reaction. The problem with the student 2 is he had an excess, he had too much of the iodine. So the way we can find the amount left over is, therefore, mass of the iodine in excess can be found by mass of the iodine, so right to I2, that's given, minus that, the mass of the iodide that's reacted. Does it make sense? Okay, we only have the we count for the amount that reacted in here. So in excess, amount left over is 450. That's a given, minus the reacted amount 380.7 grams here like this. Then you simply deduct the value 450 minus 380.7. You get 69.3 grams in 1 decimal point will be left over for the iodine. Good, okay. Remember that if we have a fixed ratio, later on we're going to use that for calculating the moles too. Question B. One student measures the 11.5 grams of sodium and reacts with the 126.9 grams of iodine, which is all consumed, producing the 138.4 grams of this sodium iodine. So let's write it down, result in this form now. Solid, iodine solid, producing this NaI solid here like this too. For the student 1, the value he used was 11.5 and 126.9 grams. Adding that making into the 138.4 grams. So this is like perfectly balanced, that we have a given amount of the reactant all completely used to produce same mass of the product side of too. That's using the conservation mass too. Now, second student measured the 15 grams of sodium and react with the same amount of iodine. So what he was given now is, instead of the 11.5, he used 15 grams and reacted with the same amount of the iodine, which is this. It produces that same amount of the product, 138.4 grams here like this. So the way we can think about that here is, again, to find the mass of the sodium in excess, we can use mass of the sodium that you are given minus that mass of the sodium that is reacted. Now, given amount is the amount actually you're given to you, which is 15. Reacted amount is from the ratio, from the fixed and complete reaction, 11.5. Bit of logical sense, and they're giving you the 3.5. Now, how many sig figs are we given? That is 3 and 3, so just leave that to the 3.5 grams in 1 decimal point. Okay, not too bad, not too hard. Okay. Now, application of these is something that we use in something called a density. Okay, density is similar to like kind of viscosity. It's how dense the object in a given volume. So, think about 1 milliliter of water. Let's use that. Density is simply the measure of the how heavy the solution. So, for example, water, H2O, has density, D value is 1.0 grams per milliliter. This means for 1 milliliter of water, the mass is 1 gram. As we kind of take, if you have 1 liter of water, we take the 1 kilo. Okay, same reason there too. So we kind of use the water as kind of our standard for now. Densities, yes, you might need to know the water density, which is 1 to 1, but just it, that's it. You don't need to know any of the density formula, density like values, but it's good to know that density is found by D, which is M over V. With M, it stands for units of the grams, volume for the milliliters here like that. Or sometimes gram per liter. So it really depends, it's all the grams per liter too. So for the water, if you have 1 gram of the, 1 liter, 1 liter of the water, that would be 0.001 gram because it's 10 to the power minus 3. Okay, milligrams in terms, it's 1 kilo is, yeah, so 0.001 kilograms then. Or 1,000 grams in that case. Okay, how do we use that? We can use the formula used to find something like this. Let's go for that 1.3. 1.8 kilo of the glucose from the sugar cane is fermented in anaerobic conditions at 25 degrees Celsius to produce 1.167 grams liter of the ethanol. The other product form is carbon dioxide. So determine the mass of the ethanol produced, and hence using the law of the conservation of mass, determine the mass of the carbon dioxide produced too. First, write it down, the balanced chemical equations. So we have C6H12O6. Anaerobic means that without the presence of the oxygen. So it goes straight, the AQ, producing the ethanol CH3CH2OH, AQ, and also producing the CO2 gas. Balancing, okay, or guys, instead of that, you can actually write a C2H5OH if that's helping you better to balancing these equations. They're the same. Okay, one is more like a molecular structure form, this is like a condensed forms. So to balance that, in terms of the number of the oxygens, we have a 3, with 6, 12, so let's matching that number of the hydrogens, with 6 times 2, or actually more, yep, times 2. Carbon 6, we have a 4 times 2 to make the balance of the carbons. And oxygen would it be 2, 4, now it's balanced. Okay, now you're not given mass in this case, so let's write it down what you're given. The volume of the glucose, C6H12O6 you're given is 1.800 kilogram. Now, when you're writing down the values in your answer sheets, make sure you include that sig figs given too. Okay, so don't just leave it at the 1.8. Show all the relevant sig figs in here. So we're going to use that in the calculation too. So that and the density of the glucose, ethanol, let's write it down the volume of the ethanol too. C2H5OH, the volume the ethanol produced is 1.167 liter here as well too. Okay, then let's do that. The density of the ethanol was given as the 0.789 gram per milliliter. When you're using those, the reason why you're copying those as relevant information is we want to see that whether your units are matched or not. This is something that's very important in science, that you need to match the unit. You're given the liter and you're given the milliliters forms in here. So I need to match these values. So what I do is I'm going to convert that into the milliliters. That is 1.167 times 10 to the power of the 3 milliliter. Okay, converting the milli to the liter, milliliter to the liter, just need to times 10 to the power 3. Going backwards, 10 to the power minus 3 here like this. Anything for the milligrams to the grams would be 10 to the power minus 3 relationship. Okay, kilo would be another 10 to the power 3 from that too. So a bit of unit conversions. I probably learned it in the mathematics before. Now that means that we can now use this. So bring that as a density. D is equals to M over V. Show that relevant formula that you're going to use. Then M is basically D times V, modified formula. Therefore, mass of the C2H5OH would be dV, which is 0.789. That times that 1.167 times 10 to the power 3. This is only possible because we match the units that you're given. Okay, then using your calculator, you're to get 0.789 times 1.167 times 10 to the power 3. You get 920.763 grams, following to the grams given you here. Everyone good up to this stage? Okay, not too bad. So you just unit conversion there. Now, you need to see that the units you're given for the sorry, that wasn't volume. Sorry, my bad. This should be a mass. Mass of the glucose, sucrose, was given at 1.8 kilograms. Mass of the ethanol was grams in here too. So what we do, you need to convert the kilograms into the grams to find into kilograms or the grams form too. So this is same as what? Times 3, 1.800 times 10 to the power 3 grams, or simply 1800 grams or two. But just leave that for the specific forms for now too. Then, time to use the conservation of the mass. So write it down as according to the conservation mass. You just say that mass of the C6H12O6 is equals to mass of the ethanol produced, C2H5OH produced, plus mass of the CO2 produced here like this. Okay. Now, once you got it up to this stage here, you can find that determine the mass of the carbon dioxide. So mass of the CO2 is therefore mass of the C6H12O6 minus mass of C2H5OH there. We found everything. It's given that 1.8800 times 10 to the power 3 minus 920.763 here like this. Now, calculate with some exact values first, and then we're going to fix that into sig figs required. So 1.8 times 10 to the power 3 minus 920.763. You'll get 879.237 grams. Let's check the sig figs that you have. You have 4 sig figs with a 3 decimal point. You have how many sig figs? 1, 2, 3, 4, 5, 6. 6 sig figs there. Okay, now following to the smaller sig fig or smaller decimal point, and you're subtracting that. So you see that 3 decimal, 3 decimal. So your answer must be 237 in 3 decimal points. Okay, now, with the questions provided kilograms in the question there, you may need to show that in the unit of kg over here. But the way you can show that is pretty simple. If you remember, like in the unit conversion from grams to kilograms, Or think about grams are lighter than, smaller than the kilogram. That means 879.237 times 10 to the power minus 3 kilograms in 3 decimal point. That's the easiest way. You don't need to actually think about all point something. Okay, that's how we can show it in the 6 fixed points using our unit conversions as well too. Okay, so density is something that we might get, you might get in the mass conversions too, but after we found that in the grams using the density, the rest of the working out is something very similar to what we've done today. So this is actually known as the mass to volume stoichiometry. Instead of using the volume, we're using the density of that liquid to find the mass converted to the mass. So in general, this is basically mass to mass stoichiometry again too. Any questions about 1.3 or the densities? Okay, let's do one more questions. 1.4, I'm gonna have a break after this. Try 1.4, please. Okay, so hydrogen peroxide is strong disinfectant and is also used in the hair bleaching products. The production of hydrogen peroxide can be simplified as H2 plus O2 producing H2O2 in the liquids. So you're given that 0.04533 liters of the hydrogen peroxide is now produced from the reaction between 4 grams of the hydrogen gas and unknown amount of oxygen. But sufficient means that it's enough to get the reaction through. And the completion means that there's no excess, there's no reactants left over. So at the end, you have 0 reactants, all that converted into or produced into the product forms too. Then determine the mass of the hydrogen peroxide produced. And then hence, they using the law of the conservation of the mass, determine the mass of the oxygen gas consumed there too, okay? So using the density, which is 1.5 gram per milliliters, make sure you convert the units, okay? You may convert the unit of the density or you may convert the unit from the volumes over here, doesn't really matter. Okay, so what I got here is the liter of the volumes, so that converting into the milliliters, 10 to the power 3, that's it, okay? Don't think to overcomplicate it, just time 10 to the power 3 or 10 to the power minus 3 to get the unit conversion right. Okay, then what you do is after we're matching the milliliters times these two values, then you should get times 10 to the power of the 3, 67.995 grams of that hydrogen peroxide is now produced. Did you get it up to this point? Okay, so mass of the H2 that used was 4.8 grams here. Again, according to the conservation of the mass, you just say the mass of the product. Let's write it down in this form too. Mass of the H2 plus mass of the O2 producing into mass of the H2O2 goes like this. So to get the mass, therefore, should be equals to mass of the O2, therefore mass of the H2O2 minus that mass of the H2S forms. Then you'll get 67.995 minus 4.0. Now, that minus 4. Okay, show the exact values first, which is 63.995. From then, you need to consider that the sig figs. You give it 2 sig figs and 5 sig figs. If you're deducting that, subtracting the 2 different sig figs, you follow to the lowest decimal point. In this case, 1 decimal point. So your answer must be 64.0 in 1 decimal point, or the 3 sig figs in this case, units, grams. Make sense? Okay, just be aware of the sig fig rules again. We've got to practice a lot of the sig figs and a lot of the calculations, so make sure you get, do perfect on those. And because like a few years ago, I had a student lost 10 marks in the HSE trials because of the sig figs. Yeah, terrible. He got 70, by the way, because he lost 10 marks. He could get 80. And, he dropped the rankings from top to bottom. Okay, all right, so that's the end of chapter 1. We're gonna have some break and then coming back for the chapter 2. A little bit of chapter 2. We're not gonna finish a whole chapter 2 today, but I need to start the moles today. Ashley and Anna, where are you guys up to now? Are you going fast and really fast in school? You just started moles, okay. Calculating n equals to m over normal mass, just that, okay. We gotta catch that. Okay, we're gonna go ahead of that. And if you need more questions, let me know. I'm actually getting some more questions from some other syllabus, so you get that. And same for you. You need to practice. That means, I don't know, no sydney girls. You guys value the calculation questions a lot. Yeah, love that calculation, love to put the stoichiometry. paint. You mean the motion equations? How many? 3 pages. 50 questions? Okay. Can I give you next Wednesday? Yeah, because I need to actually make the questions anyways too. Do you want more questions about relative velocity too, or just the motion equations?
For now, just the motion equations.
Just for now, motion equations, okay.
Actually, I might need a bit more on static equilibrium as well. I have no idea what's going on.
Okay, I try to give you everything by Wednesday too, some practice and possibly some answers as well too. Okay, but from next week, yes, after the chemistry, I have an hour of the making up some of the module 1 of the physics contents too. So it's gonna be really tired and hungry. I know that, but if you can stay back for like half an hour to 1 hour, that'd be great because I'm covering some of the the vectors again, motion equation questions again, motion graph, which will be relevant to what you're learning in school right now. And yes, same for YR, because I know you missed out some of the module 1 contents with me, so it'll be a good chance to catch that up. Yeah, so I'll leave it at that. Guys, if you need some more questions or practice, like anything, like let me know. I will. I can send you, or like I can print you, so you can get some more practice, especially in the module 2 in chemistry and physics. You know, you need a lot of practice for that. It's not easy. Yeah, they're not easy. I told you this is the hardest. We're doing the hardest part of the year 11 for physics. Chemistry. What is hardest? Module 4, maybe. It's the hardest. I think the module 4 in year 11 is more. It's more like module. It's actually year 12 contents. You get HSC question in the module 4. So people found it kind of hard, but module 2 should be okay. Did I give you homework last week? Can I collect them? The module test 3. Oh, and about retest scheduling. Let's get it. Did you find any extra marks?
I feel like I could, but I don't know.
Oh. Yeah, I know. I feel very unfortunate. Like when you say like 78, 79, I'm like, just one more mark. But you know what? Like getting the 79 in the real school exam, it's quite different to getting 80% in terms of the emotion you get it. Even though it's a 1 mark difference. If you get 80, like you'll be like, oh, okay, that's not too bad. Okay, I can do better. But you get a 79, why? And you get the same questions from your parents, like, why 79? Why 70? So they don't look at the numbers at the back, only look at the 7. And, okay, same for 80 and 89. They kind of deal the same. They don't really think like close to 90. It's actually still be 80% range. So, getting 80% all the time makes you feel happy. Your parents be happy. Life's got to be happy too. Okay. Yep. So Ashley, Ara.
On Friday anyway, so I'll just sit there.
Okay. Oh yeah, I know you're coming on Friday, so I'll put you down for Ashley. Yeah, just the CHEM. I will get the paper ready for you. Okay. Ara, anytime?
Friday?
Friday, okay. After school?
Yeah.
Okay.
Maybe Tuesday.
Tuesday, okay. Next week? Tuesday, sure.
How many people pass?
No one.
Oh.
If that gives you relief.
No, it doesn't. There is justice passing.
I mean, it wasn't too bad, to be honest. The test paper, yeah.
There's a lot of content.
Yeah. I mean, module 1 is, I told you, like, there's a lot. If you see it from the thickness of the book, it's covering a whole lot. So it's hard to remember everything from module 1. And I don't know, like, I don't know what's going on in your schools. I don't know, like, how they're going to cover everything. So, yeah, your test, if you have a test this term, yeah, it's got to be the whole module 1. So it's good to kind of revising that. It's easy to study. Okay, Tuesday, Christine. Okay.
How long does it take?
Test, it's a 1.5 technically, but it's a retest basically, same question, exact same question, so shouldn't take more than a 1.5. Less than, takes about an hour, I guess, sometimes, depends. I know many people memorizing their multiple choice answers though, but don't do that.
You didn't give us the multiple choice answer.
Did I? In purpose, yes.
Oh, no. We didn't.
No, I don't know, I won't give you that.
I don't know what I got wrong then.
Ask me. Ask me. Ask me. Okay? Because I realize, sometimes I do, sometimes I don't, but I don't really want you to memorize the A, B, C, the patterns. I can see like people are memorizing the right, like 10 seconds before the test. Okay, and then I'm done. Let's start. Okay. Don't do it. It's not really helping you at all. See.
Because I get like 3:40 and I have something at 5.
What day?
Wednesday, Thursday, Friday.
Wednesday, Thursday, Friday.
Yeah.
Do you have the tuition like at 5 and near here in the institute?
Yeah, it is good.
Yeah, I think that's you can do that like in an hour, like Thursday. Yeah. Ria. RS coming on Friday. Thursday. Okay. Put you down. Guys, retest is, I really think that retest is something that's very important because, let's be honest, if I don't have a retest, if I don't have the retest, would you ever look at the paper again? I mean, yeah, I know some would do, but in majority, like a 99%, like you will not ever look at the paper again because you don't want to see that mark, you don't want to see the red crossed it out, like you'll be like, oh, why did I do that? You're not reflecting it. Okay, how many people actually making the notes for the some question you got wrong? Yeah, thank you. Yeah, okay. There we go. Okay, unless you're doing that, unless you're like writing the questions you got wrong in the exam or like some topic test, this is something that's really important. And I strongly recommend you to do it, writing down the question you got wrong, writing down all that the contents you don't understand at the point, because at the end in the exam preparation, you only need to look at that. You only look at the question you got wrong, the question you made a mistakes. And that's really helping you to improve. It's like going up the stairs. Okay? It's not going like gradual. It's not an escalator whatsoever. It's actually going up the stairs, and that requires a bit of like, some pain, I must say. It's a painful. I know how painful it is, but it's something that's very important. Same for mathematics, same for like English probably. You're writing in English, you got to check. You need to look at it. You need to accept your mistake, you need to accept your fault, and then you improve it from it too. Otherwise, you will be staying in the same levels every single time, and that's not good. Okay, so see you all for the retest next week. Interesting. Okay, that was okay. That's okay. Homeworks. I didn't get the homeworks from you, and you.
I didn't get homework.
Did you?
She left early, so.
Lucky you. Okay, I'll give you the prints of the homeworks that we had last time then. Okay, I'll do that. And, oh yeah, I forgot to give you homework yesterday. Biology. Uh-huh. Finished? Didn't bring it, or which one did you bring? What is that? Oh, that's ages ago, but I can see it like that, okay? Now, when you're coming back to retest on Thursday, can you bring that too? And I know you're not studying in module 1 in school now, so it's quite irrelevant to do the test, but if you get a yearly test, you get a question from that too. So let's try it, okay? Even though you don't pass that, get 80% for now, just keep trying it, and one day you will see like you actually improved this much. I can see some improvements. I can actually see some improvement from you that before you started in here, yeah? So you're doing well, Just keep doing what you're doing, okay? I would tell you a time that when you need to actually sprint, do some more work, that's more likely in the exam period, okay? For now, focus on that, but let's focus on the moles and the concentration, these calculations too. Say for you, Ashley, I know this is a bit irrelevant to your school, because module 1 contents, but you know, you get those questions yearly anyways, so that's what I'm saying. I don't know how your school's going to deal with those module 1 contents. It's either they're going to rush it, they're going to rush to finish everything. They're going to skip lots of the content in the beginning. Yeah. Yeah. So it's weird. I mean, like, oh, that's making the students get confused all again too. Makes sense to some extent, because the reason I don't like the module 1 is too much theory based. Not really relevant to some contents, including in module 2 and 3 and 4, like Schrodinger's model. We never use that again. We never ever use that again. Yeah, but still we're learning it. All right, let's start module 2, chapter 2, please. We're gonna do about half of the module 2, the chapter 2. Introducing the known content known as the mole. Okay, the mole is, okay, somebody told me on the Monday class, the animal, the mole. No, okay, the mole is something that we have to understand in this here. Let's think about in terms of the, what we call the packaging units. Now, we're using lots of, not a lot, but we're using some of the packaging unit in the everyday life. So the reason for the unit packaging unit is we want to simplifying the complex numbers into the simpler or smaller terms, smaller numbers. So a good example of the packaging unit we're using dozen. We're using dozens, okay? Anna, if I say I have a dozens of crayons, how many in the dozen? There'll be 12. We know that because we made a promise, even like we kind of made a promise that, okay, let's call that 12 as a dozen from now. So instead of saying the 12 all the time, if you think about 12, that's actually odd number too. I mean, that's kind of a weird number. So, you know, it's not a 10, it's not 100, it's 12. Where is a 12 coming out from? I don't know. But we decided to call the 12 as a dozen from 2. So it's giving you some simpler term. After we saying the dozens at 12, we've kind of made a promise. We know that 2 dozens would be 24. Simply times the 2 of that. So that's how we call the packaging unit. What about couple? When we say couple, that a couple of shoes, couple of teas, or it means 2. So instead of saying the 2 all the time, we're saying, oh, we have a couple of something. We have a multiple couple of something too. Okay, so it's a packaging unit we're using to kind of simplifying that they're big numbers into small. Now, in chemistry, we do the same thing. When we say the packaging unit of the moles, okay, moles, this means that we have, the number is quite big, by the way, 6.022 times 10 to the power 23. Yes, that number is huge. They're like, whoa, what the hell? Like, where is that number coming out from? Okay, ironically, because of the big number of the moles, because we believe that, it's going in the example here, page 29, we believe that 18 grams of the water, which is equivalent to 18 milliliters, is 1 mole of water. But do you really think like, 18 milliliters of water is a big? I mean, like, a sip of water would be like less than, a sip of water is basically 18 milliliters. Okay? Every sip of the water you drink, you're having that 1 mole of the water there. So, ironically, this number is telling you the 2 things. One, it tells you that how small the atoms are. So let's say we have a 1 mole of something, 1 mole of the atom molecules. It means, yeah, we have lots of them, but in the real day life, they're not that small. And it's telling you how many, how big the numbers of the atoms and the molecules, whatsoever chemicals or compounds. So let's have a think about the mole concept in here then, okay? So let's think about here. We have let's say 1 mole of the hydrogen. We gotta deal the same. I can say that 1 dozen. Instead of saying the mole, let's do it like this. Let's say we have 1 dozen of the hydrogen, H. Then this simply means, as we promised that dozen is 12, it simply means we have 12 hydrogen atoms. Okay, so I'm gonna do the same. A couple of the hydrogen means I have 2. So it's saying the 1 mole of the hydrogen, we say, oh, the number is 6.022 times 10 to the power 23 atoms are present in that too. Now, that number here is known as the Avogadro's number. Don't add the avocado number. Every time I say that, like avocado. No, no. Avogadro is the person's name. Important scientist. You really see his name again too. Known Avogadro's number. I should write that number. We use the symbol of capital N and A to represent the symbol of the Avogadro's number too. So instead of you repeating the 6.022 times 10 to the power 23, you can simply say, oh, having 1 mole of something means we have Avogadro numbers of the atoms too. Or maybe like having half of moles then, think about the half mole of the hydrogen, would it be what? Half of that, 3.011 times 10 to the power 23, or half of the Avogadro's number. That's how we can consider it over here. Okay, so it's basically just dealing with the packaging unit, but the packaging is something that's exceptionally big. So those who learned, like I learned from year 10, you know that how big it is. Okay, having this small, say having 1 mole of, let's think about rice. I probably told you before, okay? How big is that? Like how mole? I mean, 6.022 times 10 to the power 23 about rice. Okay, how small? How big is this? How big is a rice? I'm talking about the rice, each of the rice that you're having. Okay, yet that's small rice. Now, having a 1 mole of rice, approximately having a 1 mole of rice means that you can cover the whole Australia in 3-meter height with the rice. How tall is 3 meters? This is about 3 meters there. So this height, not the Sydney, not the Houston, the whole Australia continent with 1 mole of the rice. Can you imagine? Yeah, that's a huge. I'm talking about a really huge thing. 10 to the power 23 is that big number. Okay, so this is why we don't like to use that number again and again and again because it's too big. So instead, this is why we use in the packaging unit called the moles from now on. Does it make sense? Now, before I move on to the next question, let's quickly think about, we did that in module 1, the difference between atoms, molecules. Christine, what's the difference between atoms and molecules?
Atoms have a single.
Single.
And molecules have multiple.
Multiple atom. Yeah, they're chemically bonded. So in multiple, and like this, the forms of the single would be that, and multiple forms like this. Okay, this is talking about in terms of structures there. Then have a think about here. In H2O, how many molecules? There would be 1 molecules. But how many atoms? We have 2 hydrogen atoms and 1 oxygen atoms per that too. This is a trick that you will get a lot in this type of question there too. Okay, so let's have a look at the questions 2.1 given here. Page 29, please. First of all, calculate the number of the molecules in 3.5 mole of the water. Now, one thing you have to realize is unit mole is not the molecules. They are not the same. Mole means that packaging, as I said, packaging unit of the 6.02 to times 10 to the power 23. Molecule is about the structure of that atom, the chemicals. So do not mix use that molecules and moles. I don't want to see like, oh, there's a moles of this many here, but that many molecules. No, that's not. Some people say, oh, isn't that just this on the same? Isn't that like the unit of the molecules? And I'm like, no, that we don't really like abbreviate the molecules. Okay, so having the 3.5 moles, think about here. We are given that the number of the H2O. This is how we can write the symbol, the capital N. Sorry, small n. The small n stands for the unit of the symbol of the moles. This is for the symbol of the mole. That's small n. It's given as 3.5 mole here like this. I just rewrote it like the questions were given. Then, to find the total capital N, okay, the capital N is representing the total numbers that we have of the H2O, can be found by, remember that in per mole it has 6.02 to 10 to the power 23. If I have a 3.5 moles, means that it'll be N times the Avogadro's number. So that'll be what? 3.5 times that given 6.022 times 10 to the power 23 is how we can find the total number of the molecules. The 3.5 times 10 to 6.022 times 10 to the power 23. Then you'll get 2.1077 times 10 to the power 24. Now, how many suffix? 2. We are multiplying the two different suffixes, so you need to follow the lowest suffix you have, which is in this case 2 suffix. So the answer must be 2.1 times 10 to the power 24 units, not mole, molecules for your final answer there. Don't leave your answer to moles. It should be written in units given as the molecules. Easy, okay, showing the 2 suffix as well too. 2.2, then how many oxygen atoms in 2.5 moles of the oxygen gas? So remember 2.2. Remember that per O2, for one O2, there are 2 oxygen atoms. Okay, if I have one O2, that means I have 2 oxygen atoms attached. So the way we can think about the number of the atoms first is start from here. The total number of the oxygen is therefore can be found by N of the O2 times 2 times sorry guys. The camera is a bit playing up. Okay, fixed. Okay, so total number of the oxygen atom can be found from NO2 from the molecules times 2, because we know we have a 2 per molecules times that Avogadro's number here like that. So that's given as 2.5 times 2 times 6.022 times 10 to the power 23 again. Put that in your calculator then, 2.5 times 2 times 6.022 times 10 to the power 23. You'll get 3.011 times 10 to the power 24. Now, sig figs. You're given 2 sig figs from 2.5, so you need to fix that into 2 sig figs, which is what? 3.0 times 10 to the power 24 units atoms into sig figs there. Again, be aware of the writing the correct sig figs. You might get it wrong if you're writing the wrong sig fig or leaving it in the exact values like that. Okay, now could you try for 2.3, 4, and 5? Give you about 5 minutes to try these questions. They are relatively easy. Write this formula here, so you can use that. Total number is times n times Avogadro's number here, like that. In other words, number mole can be found from total number divided by Avogadro's number. The way we can think about the question 2.3 is the same as if I have 60 crayons, then how many dozens in that? It's a kind of actually the similar style of questions. So if I ask like, 60 crayons, how many dozens? Then you simply 60 divided by 12, which is the packaging units of the dozen. Then you would know for 60 crayons, it would be same equivalent to 5 dozens there. So we do the same thing. This in short in the formulas. The number of moles can be found by total number of the molecules or atoms divided by the Avogadro's number in the same sense. Does it make sense? Okay, remember the 60 crayons, 5 dozens, the way we can convert that. So you're given now 2.5 times 10 to the power 22 molecules of ammonia. The question is asking you to find the moles, not the molecules, moles. So bring that N of the ammonia. This can be found by total number divided by Avogadro's number. That is 2.5 times 10 to the power 22 divided by 6.022 times 10 to the power 23. I recommend to memorize the Avogadro's number too, because just like a pi value, 3.14 you're using. 2.5 times 10 to the power 22, that divided by 6.022 and 10 to the power 23, you're to get 0.0415. Now, given the sig fix of 2, you need to fix that in a 2 sig fix, that is 0.042 moles with the units in 2 sig fix like this. Okay? 2.4. Calculate the amount in moles of the hydrogen atoms in 3.6 mole of the sulfuric acid. So, H2SO4 per, that's right here, per H2SO4, there are two H atoms are present in there. Okay? It's giving you the clue that, oh, how many hydrogen atoms we can find if we have a moles of that. Does it make sense? Also, the total number of the hydrogen, not the H2, hydrogen, are 3.6 moles. Sorry. Then have a think about it. If you have a 1 mole of that, for 1 mole of that H2SO4, that would be 2 moles of the H atoms too. It's simply giving some kind of ratio. If you have a 1 H2SO4, we have a 2 hydrogen. If you have a 1 mole, we have a 2 moles. Or if you have a dozen, 2 dozens. Goes in that order. Does it make sense? We're following to the some of the ratio between hydrogen and sulfuric acid. Therefore, we can, if you have, you can write like N of the hydrogen would be 2 times the N of the H2SO4 in terms of the formula and the relationship. This is then, we have given the number of mole of the sulfuric acid is 3.6. So 2 times 3.6 giving you 7.2 mole in 2 sig fix. That's it. 2.5, calculate the amount in moles of the hydrogen atoms in 0.75 mole of the water. Again, per H2O, how many oxygens, moles of hydrogen atoms? There are 2 per 2 hydrogen atoms there. Again, we can think about it. The N of the hydrogen is simply then 2 times N of the H2O straight away. In terms of relationship, so 2 times, how much we're given? 0.75 times 0.75, you're given 2 sig fix, matching that 2 sig fix, 1.5 mole, straight away. Okay, this is how we can use the moles, like using the packet, dealing with the packaging units. So do not get afraid of using the moles and or the Avogadro's number from there. Okay, any questions about finding number of moles? Just be careful with the atoms, finding molecules. You will get some questions about finding atoms and molecules. If you have a module 2 test, you'll definitely get some questions about it. Whether it be a multiple choice, at least one question in the short answers. Okay, all right. Sig fix rules, have a read through. It's actually giving us some clue. All right, then let's talk about this molar masses. Then where do we actually use those moles? I mean, yes, we kind of understand that like a mole is a big number, 6.022 times 10 to the power 323. We get it, but where do we use it? How do we use it? It's a problem. So Avogadro, which is actually the one that actually found Avogadro's number, used the carbon. He used the carbon. So what he found out was, Avogadro found out in for 12 grams, 12.0 grams of the carbon, he found it out that, oh, it's actually having it says there are 1 mole of the carbon atoms present there. So it was his experiment. He collected 12 grams. It's quite interesting, but long story short, he found it out. Oh, when he counted it, he didn't really count it, by the way. When he saw that number of the moles of carbons in the 12 grams, he found it out there was actually the 1 mole. In other words, for 1 grams of the carbons, it would be 1 over 12 mole of the carbon was presented there. So where is this coming out from? He used the mass number of the element to determine that, the moles. So where is the 12? 12 is actually the mass number of the carbon. And he found out that is not only for the carbons, all other elements having that. For example, for 16.0 grams of the oxygen, that'll be 1 mole of the oxygen. Okay, if we could collect the for 63.5 grams of the copper, it was actually 1 mole of the copper as well too. And he thought about like what would be the difference between that two. This is required, which is why you need to understand atomic structures there. Okay, having the mass number 63.5. Think about the mass number. The mass number is telling you the number of the protons plus number of the neutrons, as we discussed in the module 1. And having a different mass number means that they have a different masses in each of the atoms. So carbon has mass 12, oxygen has 16. So even though we have the 1 mole, which is the Avogadro number of the carbon and oxygen, because each of the carbon has 12 masses, each of the oxygen has 16 masses, their weight is different. Okay, it's the same as like if it was the same boxes, number of boxes with a different type of shoes. We have a slippers and a sneakers, or some of the shoes, leather shoes. Each of the individual boxes are way different here. Means that having dozens of the boxes will actually give you different masses. If you have dozens of the leather shoes compared to dozens of the slippers, that'll be heavier because individual boxes would have the different masses included. That's how he thought about the mass, and actually he calculated and found out the carbon. Interesting about the thing is, the reason why he picked the carbon is known to be the most non-reactive. So he used a graphite, and the diamonds in this case, okay, more like a graphite. The most non-reactive element he could have used to test other metals and non-metal, they have a certain like a reactivity. So it was a little difficult to measure that. So from then, he was able to measure this. Oh, okay, let's use the mass number to determine that something known as molar masses. Molar mass. In short, we're using the capital M and M. Some textbooks, some schools probably use just the capital M to show that. I prefer to use it in the MM in this case. It has the unit of the gram per mole. Remember this unit. Remember this unit. You might get a question asking to find the molar mass. You need to leave your answer in the gram per mole, even though the unit's not given. But where is that unit coming from? He found that out, like from the mass numbers, the relation between number mole, okay, number mole, let's go like this. Number mole is actually same as mass in gram divided by molar mass in gram per mole. Here like this, okay? Well, the molar mass is simply all the mass numbers of using the periodic tables. So you actually need to get some periodic table today. We're going to use this. 2, 3, 4, 5. Okay, here. All right, could you pass that? Thank you. So what we're using is, we're using the exact mass numbers given in your periodic table. That's an isotopic masses too. So for example, hydrogen, don't use 1, it'll be 1.008. Carbon is not 12 exact, it's a 12.01. So we're using exact values. The way we can find the molar mass is pretty simple. So for example, if I ask you to find the molar mass of the carbon, it'll be 12.01 gram per mole. That's how we can write the molar mass. Okay? Same here, molar mass of the oxygen would be 16. Using that value in your periodic table, 16.00 gram per mole here like this. We're using the same method to find the mole for the compounds like ionic compound or the covalent compound. So if I ask you to find the molar mass of CO2, remember that CO2 is made with the 1 carbon and 2 oxygen. So it would be mass of the carbon plus 2 times mass of the oxygens like this. Does it make sense? Giving you what? 12.01 plus 2 times 16. giving you 32, therefore 44.01 gram per mole. This is how we can find the mole, something known as a molar mass, or molecular mass, sometimes it's used to, but let's use that molar mass for now. Okay, because molecular mass is kind of limited terms that we can use. So using that, think about the relation between the moles and that. Now we are able to find that how many moles are presented in the given solid. This is for solid only, by the way. Solid states only. You can't use for the aqueous, you can't use for the gases. We will learn that in different chapters. Chapter 3 and 4 is for the different way we can find the number of moles. Okay, why? Because we can't weigh. Yes, we can weigh the amount of the solution, but it doesn't really give a pure. So the pure solid state in this case too. So how do we use that? Page 33, question 2.6, please. We're using this to calculate the number of moles easily, or find the amount of the mass of that. So calculate the mass of the 0.35 molar of the magnesium nitrate. Okay, on here, next to the N equals to M over M, or N equals to M over molar mass, can you write it down? Mass is equals to then N times the molar mass in terms of the modified formula. Basically the same thing, but we gotta use this. So for question 2.6, the way we can show the type of work you need to show that is, you gotta start like here. Mass of the magnesium nitrate is found by N times the molar mass. Make sure you show the relevant formula that you want to use. After you wrote that, show the number of moles, 0.35. Then show all the relevant working out to find the molar mass of the magnesium nitrate. So how many do we have? We have per magnesium nitrate, we have 1 magnesium, 2 nitrogens, 6 oxygens. Does it make sense? So in your bracket here, show that mass of the magnesium is known as 24.31, mass of the nitrogen known as 14.01, and mass of the oxygen is 6 times 16. This is the working out required, not only for year 11, year 12, up to the HSC, maybe in the university as well too. Okay, that's how we can show the working out. Make sure you show that every single time. So 24.31 plus 2 times 14.01 plus 6 times 16, that times 0.35, you to get 51.9155 given. Now, given the sig fix of what? We have a 2 sig fix given, fixed and a 2 sig fix, therefore it's a 52 grams into sig fix. This is how you can find the answer for question 1 in 2.6. Markers will actually look at this. We do. If you just use a calculator to show the values in the calculation and then you're working out in here, you lose mark. And generally, this is only 1 mark question. Okay, I show you what. Not showing this, losing 1 mark. Not showing the sig fix, you're losing 1 mark. Not putting the grams, you're losing 1 mark, even after you complete it and you get the right value. Okay, this is why we say the chemistry teachers that pickiest markers in your school. Maybe English, I don't know. Okay, depends, but we really mark harsh on your sig fix and calculations in the chemistry. Okay, just be careful. You've got to practice a lot of those sig fix and calculations. Next one, calculate the mass of the 4.68 moles of sodium carbonate. Then the similar method we can use. That we have mass of the sodium carbonate and CONO3 would be same as N times the molar mass. Make sure you show the relevant formulas here. That's giving the moles of the 4.68. That times molar mass of everything. So in your big bracket, show that 2 of the mass of the sodium, 22.99. That's a molar mass of the molar mass of sodium. 1 carbon and 3 oxygen. Okay, and after you do that, simply use a calculator. So 2 times 20.99 plus 12.01 plus 3 times 16 that times 4.68, you get 496.0332. Now, what I recommend when you're working out is show the exact values first and show the conversion into the sig figs you required. You're given 3 sig figs. So from that, it'll be 496 grams in 3 sig figs. Oh, in here, don't use the approximate. Okay, if you do that, you actually get it wrong because this is actually in the exact values in 3 sig figs. This is how we can do the unit conversions. Make sense? Okay. Okay, try for the next 2, please then. What about those 2? It's a combination of what we learned in the previous chapter. Okay, so mass of the carbon dioxide you're given for first question is 22 grams. Question's asking you a number of the CO2 from it. Now, there is no method that we can find the number of molecules straight from the masses. So you need to use the number of moles, you need to find the number of moles initially. So from that mass, you can think about N is equals to CO2 must be equals to M over molar mass in terms of formula. That would be 22 divided by 12.01 plus 2 times 16 under the numerator. The denominator there. Okay, this is the required working out, by the way. Okay, guys, check your working out whether you wrote everything on the board too. I mean it. You will lose a mark if you're not showing the formula. You lose a mark. You're not showing the substitution there. We mark it really harsh. We do. So that is now 22. So 12.01 plus 2 times 16, and 22 divided by that, you get 0.498998886. For this value here, try to write it in like some more exact values if you can. I can extend it to exact values because that's not a sig fig yet. We need to minimize that sig fig errors later on too. So write it down as a mole, first of all. And make sure you save your values on your calculator because we need to use that again. After that, you got to think about it. The total number of the CO2 is found from n times that, the Avogadro's number there, which is, we have 0.4998886, that times the Avogadro's number, 6.022 times 10 to the power 23. So from your saved up your value in your calculator, just simply times answer times that 6.022 times 10 to the power 23, you'd get 3.010 times 10 to the power 23. Now, fix that into the given sig figs of 2. Your final answers then must be 3.0 times 10 to the power 23 molecules in 2 sig fig. This is the final answer then. Next question. Calculate the number of the sucrose molecules in a teaspoon of the sucrose. So C12H22O11. Let's write it down. So mass of the C12H22O11, that's given as 4.2 grams. Check the sig fig is given as 2, so be mindful of that. Then with the same method, number of this sucrose H22O11 can be found by mass of a molar mass. Show the relevant formulas. That is 4.2, and here 12 times 12.01, as we have 12 carbons, plus 22 times 1.08 for the hydrogen, and 11 times 16. That's now put it in your calculator. 12 times 12.01 plus 22 times 1.08 plus 11 times 16. Okay. 4.2 divided by that, you'd get 0.01227 mole in like more exact values. Then number of the mole, the C12H22O11 must be n times the molar, the Avogadro's number here again too. That is 0.01227. That times that 6.022 times 10 to the power 23. Here like that. So from the save the value again, you're to get 7. Let's fix them to sig fig straight away. 7.4 times 10 to the power 21 molecules again into sig figs. Easy, okay? So it's kind of repetition of the what we're this kind of working out again and again, and surprisingly, you actually see that quite a lot in the year 12. Yes, year 12, you see that quite a lot of those calculations too. Any questions up to here? All right, let's do up to the empirical formula today. We're going to leave the molecular formulas after that. So using the number of the molecules or the number of moles, we are able to determine something known as empirical formula. Now, what is empirical formula? It is the formula that the simplest form of the whole ratio. Please highlight that the empirical formula of the compound gives the simplest whole number ratio of the element in that compound. So given some formulas here, if we have a molecular extra formula, is given P4H10, empirical with P2O5. So you may think like molecular formula is like your full name of spellings. Okay, empirical is like an initial of this your names there. We're kind of ignoring, canceling all the irrelevant, like, and we're canceling out the numbers. So you see that C10H22, if that's a real like a formula for these molecules, we can just simplify that into the C5H11, which is the empirical formula. Then how do we use that? How do we use that to find the number of moles? In general, you will be given the questions like given the certain mass of that. In this case, we're using this. So I'll show you the example on the next page, please. 2.8 a compound of the carbon and oxygen contains 27.3% of carbon and 72.7% of oxygen by mass. By mass, by the way. Then calculate the empirical formula of the compound from it. So we need to find the simplest ratio between the carbon and hydrogen. But carbon and oxygen, we can't use the mass to determine their empirical formula because empirical formula depends on how many molecules, how many atoms we have. Remember that having an individual carbon and oxygen would have a different mass numbers. Mass numbers there. So in different packaging, like the boxes of the shoes are there too. So we can't actually get the ratio of the masses to determine the empirical formula. This is the reason why we need to use that the number of moles to find it. So the way we can solve the question is, there's two methods. I'll show you one method here. Assume that, for this question, 2.8, assume that there is 100 grams of the molecules. We kind of make an assumption here. Then, what would be the mass of the carbon if we have 100 grams? If I have 100 of the combination of the carbon and oxygen. 15? Oh. Oh.
27.3 over opposite times.
I mean, this stuff over here. I'm just simply asking you, if we have 100 grams of compound, because we know the percentage, the mass of the carbon in the compound must be 27.3 grams. I'm using the percentage. Does it make sense? Okay. Mass of the oxygen is then rest 27.7 grams because we know the percentage. We know the percentage there. Does it make sense over here? Then, from the number of mass given here, you can find the N of the C, N of the oxygen, using that mass over molar mass. Say mass over molar mass again too. This is 27.3 divided by 12.01, and 72.7 divided by 16 goes like this. Then what do you see? The total number of mole is 27.3 divided by 12.01. You get 2.27 mole is presented, and that's at 72.7 divided by 16. You get 4.54 mole. It's now in that number of the grams. So what we have done here is, from the mass that we cannot directly compare because they have the different mass numbers, we converted it into the number of moles that we can directly compare to each other. We now can compare the quantity, how many of the oxygen, how many carbons that we have in that given compound. Then what you do after is you divide it by the smallest. That is 2.27 divided by 2.27, because between these two, small is small, I should say, small is small, then giving you 1. 4.54 divided by 2.27, giving you 2. This gives you then, therefore, the mole ratio of the oxygen, carbon to oxygen. Carbon to oxygen is 1 to 2. This gives me that, per the compound we have 1 carbon and 2 oxygen. So therefore, the empirical formula would be CO2. It doesn't mean that this is a molecular formula. It might be C2O4, it might be C3O6. We don't know. We can't find it further from here. But what we can get the simplest form, the formula is CO2, using the moles. And this is a rule that you can use. And this is also be given some guideline to give it on your page 35. What are you doing to do? Obtain the mass of each element in the compound, and then calculate the amount in moles of each element presented using the N equals to M over M, and convert the mole of each element calculated in the previous steps to a whole number ratio, and then write the empirical formula. That's kind of step-by-step guideline too, or this is the kind of template they can use for every single empirical formula questions. Now, using that template or the guideline over here, could you do the next question then, please? Remember that the conservation of mass too. Okay, first of all, according to the conservation of the mass, that we know that mass of the reactant must be equal to the mass of the product if there goes complete reactions. In other words, as you're given the mass of the magnesium, which is one of the reactants, and the mass of the product, which is 1.96, you are able to find the chlorine mass. That would be 1.46 grams as is shown. Okay, you got to start from here then. What I'm going to do, I can actually make in the tables too. So for the magnesium and chlorine, I can construct a table. Okay, the mass in grams is given as 0.50 and 1.46. And number mole and mole can be found out by using the m over molar mass. That's 0.5 divided by the magnesium. Hang on, 24.31. And chlorine 1.46 divided by 35.45. Given here, that's giving you 0.5 divided by 24.31, giving you 0.02056, and this is also giving you 1.46 divided by 35.45, 0.04184 is given. Then what do you do after we find number of moles? We can divide that with this smallest moles that you have. So in this case, this is the smallest, as we know, that would be 0.02056 divided by 0.02056, giving you 1. 0.04184 divided by 0.02056, that giving you approximately 0.02056, giving you 2.00. Okay, the ratio is therefore 1 to 2. Okay? Oh, yeah, that conservation mass. Okay, therefore the ratio would be 1 mg and 2 Cl. That would be empirical formula of the mgCl. I mean, like that's basically the molecular formula as well too. Okay, you can use a table. I mean, like I like to say the table, like as long as you showed all the relevant working out like this, it's actually giving a better like working out, the same working out in this side and that side, anyways. Okay. The key point is I use the conservation mass that we learned in chapter 1. Okay. This is not a trick question because we kind of presume that you know about the conservation mass, so how much of the chlorine will be required for the complete reactions. Okay, and module 2, each of the individual content-wise, they're pretty straightforward and not that complicated. But I picked the module 2 questions quite hard later on too because they are mixing up all the questions from chapter 1, chapter 2, 3, and 4. Like I can give you questions like I have a questions like I have 10,000 like in 100 10 to the power 25 carbon dioxide there. Okay, that's reacted with something like some of the reactions too. So they can mix swap and playing up with numbers. So do not get tricked. Make sure you do lots of practice for the module 2. I know, except with no Sydney girls, you guys haven't started module 2 yet. You're probably doing in the end of the term, if it goes early, or maybe next term. Most likely week 9 of this term, you need to start the module 2 to follow up the schedules. Okay, so if we have now what, week 2, we're now going ahead up to 7 weeks. So you have plenty of time to practice that. And do not get afraid of making mistakes in the module 2. Practice as you go and get it right, and just you need to be perfect. There shouldn't be any mistakes in the calculating number of moles and some molar masses. That's all for today. Any questions? Okay. No worries. Okay. Homeworks. It's actually topic tests, but try this for next week. We're going to go through some of the questions. We're going to finish the rest of the chapter 2 next week. Oh, yeah, past that. Thank you. Chapter 2 next week, and then doing some questions related to the N equals to molar mass. And Anna and Ashley, if you guys starting the solution next week, let me know. Okay, doing N equals CV or anything about concentration, starting that, let me know. That means you're going really fast, by the way. Okay. All right, that's all. Ria, I need to give you another homework from the last week, the missing homework. See you. Okay, try that. Okay, see ya.